So in this particular, so now we're going to move on to the sort of the core of this course, right? And so we're going to start talking about equilibrium. And we'll start out with equilibrium of a point. And there's actually a lot of physical situations where this is useful. We'll start, first thing we'll say is the equation, right? So equilibrium of a point satisfies, or equilibrium of anything always satisfies this equation. If the sum of all the forces is equal to 0, then inherently, right, our acceleration is equal to 0. And so the point is at equilibrium. It's either moving at a constant velocity or not moving. And in most cases, we'll think about it not moving, right? We'll be interested in the situation where everything is sort of not moving. Inherent in this, right, if we plug in our components of that force, right, so we'll write some forces, and we'll think about it, force x I hat plus force x j hat, right? Oops. Sorry, not force x, force y j hat equals 0. We'll realize that this vector statement in 2D represents two scalar equations, right? So this is equivalent of saying some forces in the x equals 0 and some forces in the y equals 0. All right, so that gives us, right, two equations, which means we can solve for two unknowns. Okay, so one vector equation in 2D, and this is a key point we'll keep in mind, this is 2D, right? One vector equation in 2D will give us two scalar equations, some forces in the x, some forces in the y. All right, so we'll go ahead and I mean, this is in some sense the end of the math, but let's walk through an example so we can talk about how to set up and solve these types of problems, because this is really what we're interested in. Okay, so here is a frame, and we have a cable that goes from A to B, a rod that goes from A to C, and some sort of force P that's applied. We'll say P is equal to 100 pounds. Right, I'm just choosing that. There's no particular reason for that. What we want to find here is what is the force in AC and what is the force in the cable, right? If you think about it, that's a design equation, or interesting. That would be a question you would want to know if you were designing this. So let's say you were asked to design a frame that kind of looks like this, and someone gives you a piece of steel and a wire rope and says, figure out how much force I can apply at P, that's one way of thinking about it. But obviously, when we're designing something, what we want to know is what's the force in AB and what's the force in AC, so we could figure out how much steel we need and how big the cable needs to be. All right. So when approaching these problems, we want to start and think about, where do I know stuff? And where I know stuff is I've been told what P is. So we know what P is, and the things that we don't know are, we want to know what AB is and the force in AC. And these all come together at one place, point A. And so we'll think about drawing a little cut, a circle around A, and see what we cut through. And we cut through AB and AC, which is good. So we'll go over here and draw what we call a free body diagram. So we'll take point A, we'll catalog our forces there. So we know, right, 100 pounds. We know FAB acting up that way. And then I'm going to say FAC acts this way. All right, we know some geometry. We know that's 30 degrees, and we know that's 45 degrees. Okay, and we know that because it's given to us, right? Here's this 45-degree angle on AC and this 30-degree angle on AB. All right, notice I decided to pick AC pointing up and to the left. The directions that you pick these unknown forces, we don't know AB, we don't know AC, are immaterial. It does not matter. Just pick a direction, and you'll get better at picking the right direction as time goes on. You can think a little bit about how this would move, right? So if this is pulling down, this point has a tendency to want to go downward, and so P has to be pushing up on it to keep it from moving downward, and AB needs to be pulling to keep it from moving downward. And so this will come. But if you choose the wrong direction, the only difference is it's going to be negative. The final answer you come up with will be negative. The actual number won't be different. You just need to know how to interpret that. All right. So we think about our two equations, right? So we think about some forces in the x. And so that means that, right, we'd have FAB has an x component, right? And FAC has an x component, and they're equal to 0. AB is positive because if we think about when we break it into its components, it looks like that, and FAC would go up in the other direction, so that's why that's negative. And then some forces in the Y, we just catalog our forces in the Y, right? And so FAB plus FAB or FACY both are positive, and then we have minus 100 pounds equals 0. All right, so here's our 4 x components. We know we can write our component form of our vectors by saying FABX is equal to magnitude FAB, and then in this case cosine 35. No, sorry, not 35, sorry, 30. And then FABY is equal to magnitude FAB, and then that would be sine 30. And then FAC would be equal to magnitude FAC cosine 45 degrees. And then FAC, that's x, FACY is FAC sine 45. All right, then we take those, plug those in here. The only unknowns that we have here are the magnitude FAB and the magnitude FAC. So we've got 2 unknowns, 2 equations, and then you can solve them. And that's that. All right. So this is the component method of solving equilibrium problems, and it's the one that you'll do the most. You will solve these equilibrium problems in components most frequently, because almost always you will know the geometry, and then that makes the components easy to get at. There's another way of thinking about this problem, and I'm going to erase this, and we'll look at it real quick. So we can look at let's draw our free body diagram again, right? That's what that thing was called. So 100 pounds, FAB, and then FAC. And we can also think, right, we could add this using the method that we first learned with graphically. I keep saying geographically. So, right, so here's our triangle of those 3 vectors, and this would be 100 pounds, right? This would be FAB, and this would be FAC. We know this is 45, this is 30, and so we could use our cosine rule and go to our solution right here, right? We've got a sine and cosine rule, so we've got 2 equations, and so we can go ahead and create this particular solution quite quickly. The interesting thing to notice here is, right, this is a closed path. So if I were to start here and walk from here to here and then back down the 100-pound force, we end up at the same place. And so what this is a graphical description of some forces equal to 0. All right? So this is the fact that you draw a closed path of all your force vectors and end up at the same place is a graphical description of 0. And so we can write that and say all forces create a closed path in equilibrium when a body is in equilibrium. All right. And so this is a word statement of our equilibrium equation right here. Some forces equal to 0. All right. So again, what you need to think about is you need to look at the body when you start setting these up, figure out where you know something. In this case, we know P. Figure out what you want to know. In this case, we want to know force in AB, force in AC, and then figure out a place to start. And usually you start at the place you have information, then push it out to where you don't have information. So we look at this and we go, aha, AC, AB, and force P all connected A. So we'll draw our free body diagram here by cutting through member AC and member AB and replacing those members, those physical members, with the forces that they represent, right? So there's a force in cable AB preventing A from falling downward, and a force in member AC also preventing A from falling downward or moving inward or doing something strange like that. All right, and that's it. That's all there is to it for solving equilibrium of a point.